Hi, my name's Norman Fenton, and what I'm going to show you in this very short tutorial is how to solve a very commonly occurring problem in Bayesian networks. The problem can be simply described as follows. We've got a continuous node, which in AgenaRisk we normally use a simulation node for, where this node actually represents a probability distribution. Now you can say, well, every node in a Bayesian network has a probability distribution, but let's suppose that this actually represents, let's say, the probability of a particular component failing in a system. And let's suppose its node probability table, therefore, is going to be defined as a distribution over the 0-1 scale. Let's take something like a triangle distribution where the left and the right is 1, and let's say the middle is, let's say, 0.2. Okay, when we run the model, we can see the distribution there, and we can see that the mean of that distribution is actually about 0.4. Okay, now what we want to be able to do is to have a Boolean node, which when we run this Boolean node, for which the true value corresponds to the mean of this distribution. So we want to say, well, the mean probability of that component failing is 0.4. Let's call this something like component fails. So what's the chance the component fails? Well, it's going to be about 0.4. Right? The problem is we want to be able to link those and do that. So we want to be able to say that the true value here should be based on the mean there. Okay, well in AgenaRisk you could make these two separate Bayesian network objects and do the link that way, where you can actually pass the mean as a parameter. But if you want to have it in a single network, how do you do it? Well, here's how you do it. What you need is to introduce a kind of a dummy intermediate node, which is actually going to be an integer interval node. Okay, we get that warning. And we want the node states of this to just be 0 and 1. So we want to make sure that these are, so let's delete that. So we want these to just be 0 and 1, and we apply that. And now what we're going to do is make this a parent of that, and simply define this to be a binomial distribution, a special binomial distribution, where the number of trials is 1 and the probability of success is simply that parent probability. And what I'm also going to do here is actually, in the appearance of this, I don't want this to be treated as a continuous thing. I want it to be displayed horizontally, and when I do that I get the output that I expect, which is exactly what I wanted, whereby the 1 here, which you can think of as a true value, corresponds exactly to the mean of that distribution. And all I've got to do now is link these two and define this in the obvious way, the MPT here. When it's 0, we want it to be false, and when it's 1, we want it to be true. Okay, we run the model, and hey presto, we've got exactly what you'd expect. And if you enter the value here, you know, for example, if it turned out actually it was known to be 0.6, then when we run the model, you can see it does what we want. Now, of course, this node is a dummy node. It's got to be in the model, but you don't want to make it visible, right? And then we just hide it. You can hide it or see it at your wish. That's all you need to do. Now, if you open the example models, you'll see in BASIC here, we've actually got that very model. Again, there's the hidden node, and it's all explained nicely there, and you can see it. And we've actually got a nice little example also in BASIC called failure in repeated operations, and you can see where this solution is important. In fact, we use it in a couple of places because we're looking at the probability that an operation fails, and we're looking at outcomes. So we need to be able to know the mean of the probability of failure distribution.